Fermilab, we study nature at its most fundamental, drilling down to the smallest scales of matter using some of the largest and most advanced machines in the world. Accelerators, powerful microscopes, send particles barreling at near light speed into other matter, creating subatomic scraps. Detectors zoom in on those fleeting pieces, making the invisible perceptible. And sophisticated computers sweep through all of it, crushing mountains of information into gems of data. We also use our cutting-edge technology to explore the mysteries of dark matter and the quantum realm. Thousands of scientists from around the world partner with Fermilab to explore how the universe works, expanding humanity's understanding of matter, energy, space, and time. Fermilab is solving the mysteries of the universe.
Good afternoon, and welcome to Fermilab's virtual Ask a Scientist program. Today's presentation is Fermilab, A Frontier History. I am Rick Polad. I'm an education facilitator at Fermilab, and I will moderate today's event. Please type any questions you have into the chat, and we'll answer those after the presentation. And following the questions, we'll take a virtual driving tour of the Fermilab campus. Now, it is my pleasure to introduce Valerie Higgins. Valerie received her Bachelor of Arts degree in English with a minor in history from Illinois Wesleyan University in 2008, and received her MLS with a specialization in archives and records management from Indiana University Bloomington in 2010. She has worked as project archivist at Indiana University's Lilly Library and assistant archivist at the Ryerson and Burnham Archives of the Art Institute of Chicago. Valerie became Fermilab Archivist and Historian in 2012, and since 2021, she has helped manage the Fermilab Library. Good afternoon, Valerie. It's all yours.
Hi, thanks so much, and thanks for coming, everyone. I'm just going to get my screen shared here. Let me start this up. Okay, so as he said, I'm Valerie Higgins. I've been Fermilab's archivist and historian since 2012. And I'm going to give you a basic overview of the lab's history, covering some of its main organizational and scientific milestones. So if you had been on the Fermilab site a little over 50 years ago, you would have seen something like this: farmhouses, barns, and fields. So I'm going to tell you the story of how we got from what you see here to today. So what is Fermilab? Well, Fermilab is America's particle physics and accelerator laboratory. Scientists at the lab use complex, powerful machines called accelerators to study particles, the smallest components of matter. Accelerators use magnets to create beams of very fast-moving particles that can then be used in experiments. The lab tries to answer questions like, what are we made of? How did the universe begin? And what secrets do the smallest, most elemental particles of matter hold? And how can they help us understand the intricacies of space and time? So organizationally, Fermilab is run by the US Department of Energy, or DOE. It has over 1,700 employees, including scientists and engineers from all around the world and many users. And it also collaborates with many different countries on physics experiments based in the US and elsewhere. Physically, Fermilab occupies a 6,800-acre site in Batavia, Illinois. This is an aerial view of the Fermilab site, and I want to point out that prominent ring that you can see on that aerial view. That's the main ring, and you'll hear more about that later. So I want to start by talking about how the lab came into being, how and why. These are some of what I would call the prehistory milestones of the lab. The first of these was something called the Ramsey Panel. This was a panel of scientists convened by the Atomic Energy Commission, or AEC, which is basically the predecessor to today's Department of Energy. This panel was headed by physicist Norman F. Ramsey, who he would later win the Nobel Prize in Physics. And the reason this panel was organized was that at the time, there were many different ideas for accelerators at a variety of locations in the US that were being proposed. And this panel was convened to determine what the priorities for the field of high energy physics in the US should be in the coming decades. When they completed their report in April of 1963, one of their recommendations was that the Lawrence Radiation Laboratory in Berkeley, California, build an accelerator with an energy of 200 GeV. You'll hear me say GeV a few times. This is basically just a measure of energy. And sometimes you'll see it as BeV, which means the same thing. So although this lab would ultimately not be built by Berkeley, this did begin to lay the groundwork for what would become Fermilab in this April 1963 report. The next milestone happened at a meeting at Brookhaven National Laboratory in New York in June of 1963, when a prominent physicist named Leon Letterman presented a paper titled "A Possible High-Intensity, High-Energy Accelerator, the Truly National Laboratory." In this presentation, Letterman described the characteristics of an ideal accelerator laboratory. In particular, he imagined a lab that would be geared towards the users, that is, scientists who perform experiments using the accelerator facilities. There were existing accelerator labs at places like Brookhaven and Berkeley, but these favored users from their own institutions because they were affiliated with those institutions, and they didn't give equal consideration to proposals from other scientists not affiliated with those institutions. So Letterman imagined a lab that was geared primarily towards outside users, with committees that would ensure facilities and beam time were allocated fairly between experimenters. This vision would contribute to shaping Fermilab. Letterman was one of the lab's important early users. He would serve as head of the lab's users organization, and he would later become the lab's second director. In June of 1965, that Lawrence Radiation Laboratory that I mentioned earlier did produce a design study for a 200 GeV accelerator. This design study was lengthy, detailed, and expensive. The cost estimate was $348 million, which was significantly higher than the Atomic Energy Commission's original estimate of $280 million for the project. This was in part because the design was conservative. The designers did not take risks in their plans. They really wanted to make sure that their design would work immediately the first time they tried it. But it did incorporate, this design did incorporate some of the ideas about creating a user-friendly institution. So the next major task that had to be accomplished was you needed an organization to run this proposed lab. On January 17th of 1965, the National Academy of Sciences sponsored a meeting of presidents from 25 major research universities to discuss the management of the planned 200 GeV accelerator facility. So at this meeting, these university presidents decided to form a group called the Universities Research Association, or URA, to manage the laboratory. URA was incorporated in June of 1965, and it held its first annual meeting on November 7th of that year. And Norman Ramsey, who I mentioned earlier, is head of that Ramsey panel. He became president of URA in 1966. So now we have a plan for the lab, a group to manage the lab. The next step was to choose a site for this new lab. At this point, it was no longer a given that the new lab would be located at Berkeley. Instead, the Atomic Energy Commission decided to have a nationwide site competition. The AEC established the criteria by which the proposed sites would be judged, and this included things like what the cost of construction would be, whether there were adequate utilities, how accessible it was for scientists from different areas of the US, its proximity to major research institutions, and whether there were local communities who could provide human resources and housing. So the AEC received 126 proposals that included well over 200 sites in 46 different states. There was a site in Illinois that made it through to the final round of the competition, and that was the little town of Weston, which was built in the early 1960s and had about 400 residents at this time. And the Atomic Energy Commission announced that they had chosen Weston as the site for this new accelerator on December 16th, 1966. And you can see in this photo is an aerial view of Weston. This image was taken not too long after it was selected, though the lab has started to actually move in here in this photo. But you can see all those little houses that were part of Weston. Many of those houses were preserved by the lab, and in the lab's early days, they were used as office and lab space. Additionally, this was a 6,800-acre site. It was much larger than just Weston. There were also farmhouses scattered around the site, and the lab preserved many of those and moved them to that space where Weston was, and collectively, these buildings all became known as the village. So the next step was to select a director for the new lab, and the Atomic Energy Commission chose Robert Wilson in February of 1967, and he remained as director of the lab until 1978. And Wilson's importance to the history of Fermilab really can't be overstated. His philosophy and priorities shaped the philosophy of the lab as a whole, and his personality left a stamp on the culture of the lab that is still visible today. At the time that he was selected, he was director of the Laboratory for Nuclear Studies at Cornell University, and he had some great successes in building an accelerator there. His first real contact with this 200 GeV accelerator facility that was planned was actually when he criticized that Berkeley design study. He criticized it as overly conservative and lacking in imagination, and he felt that it was possible to build a more powerful accelerator for less money. He was also a very interesting person in other ways. He was born in Frontier, Wyoming in 1914. Growing up, he spent a lot of time on his family's cattle ranch, and he was a skilled horseman. He was known for having been the youngest group leader on the Manhattan Project, and he was also a talented and passionate sculptor, and he created a number of sculptures for the lab site that you'll also see some more of those later. So in early 1967, the lab was ready to start, but the Weston site was not yet ready. So they rented offices on the 10th floor of a building in Oak Brook that was partway between O'Hare Airport and Weston. And on June 15th, 1967, about 18 people arrived for work at the NAL offices at Oak Brook, which marked the start of the lab. Now, I said NAL, which stands for National Accelerator Laboratory, because at this time, that was the official name of the lab. It wouldn't become Fermilab until a bit later. So during the rest of 1967, the main task that they had to complete was creating a design report that would lay out a detailed plan for this accelerator that they would build. And so they worked on that for the rest of 1967, and that was completed in January of 1968. And it was a little later that year that the lab completed its move to the Weston site. This is an image of the flag raising ceremony held in front of the director's office on September 24th, 1968. And that is, in fact, the director's office that you see in the background of that image. Like I'd mentioned earlier, a lot of those little Weston houses were preserved. And so this was the original location of the director's offices, was one of these little houses. Actual construction on the lab began at the groundbreaking ceremony on December 1st, 1968. This was actually the groundbreaking for the LINAC, which means linear accelerator. The LINAC was the first part of the accelerator complex. It was both the first part built that they first broke ground on, and it also was the first in the chain of accelerators in this accelerator complex. So this marked the beginning of construction at the lab. You can see it was December 1st, so they had chosen quite a chilly day for this groundbreaking, but there were still many lab employees and people from the community who were present at the event. And Robert Wilson, the first director of the lab, you can see him there speaking at the groundbreaking. And also present was Glenn Seaborg, who was chair of the Atomic Energy Commission at the time. And here you can see Seaborg and Wilson using a shovel to turn the first shovel full of dirt that marks the construction of the National Accelerator Laboratory. And here are just a couple more images from that groundbreaking day. So the next major milestone was the groundbreaking for the main ring and the construction of the main ring. That happened on, the groundbreaking happened on October 3rd, 1969. You can see they had better weather for this groundbreaking. October is a little more reliable in Illinois than December. And that's Director Robert Wilson in the middle with his hand raised. So you'll remember earlier I pointed out in that aerial view of the lab recently, you can see that big ring, which is the main ring. Well, here you can see that ring starting to take shape on the land of the lab. And then you also can see some footage of it under construction here. So the main ring is an underground tunnel about 4 miles around that housed the main ring accelerator. The accelerator consisted of 1,014 magnets and was used to accelerate particles called protons to very high speeds. The scientists could then use these fast-moving energetic particles in their experiments. Building the main ring was often challenging. Wilson set ambitious schedules and goals, and once those schedules and goals seemed to be in reach, he would often make them even more ambitious. He also took design risks to cut costs, which would allow him to deliver a better accelerator. For instance, one of the biggest risks they took was that tunnel was not anchored to the bedrock on pylons. Instead, it rested on the glacial till just below the soil. So construction on the main ring continued until April 16th, 1971, when the final magnet was put into place. You can see here a few more images of the construction. I like that one on the right because there's some people standing in the mouth of the tunnel and you can really get a sense of the scale. So once the construction was complete, it did take a bit of time for the accelerator to reach its design energy. They encountered a few challenges with that, but on March 1st, 1972, the accelerator reached that design energy of 200 GeV. You can see some of the celebrations in the main control room here. That's Robert Wilson leading the toast. And then there's also some footage from that day. Part of the reason for the celebration was that the main ring was completed ahead of schedule and under budget, which was something that Wilson had promised and achieved, and it was a huge achievement. The other major achievement was that 200 GeV was only the beginning for the main ring. It quickly surpassed its original design energy, reaching 300 GeV in July of that year, and in 1976, it reached 500 GeV. And Wilson was, of course, instrumental in accomplishing this, and he won the National Medal of Science in 1973 for his work on the main ring accelerator. And I want to wrap up talking about this day with one of my favorite images from that day, which is on this screen. You can see this line that says 200 GeV, hip hip hooray. So now, of course, the point of building this accelerator was to perform experiments. So the experimental program began in February of 1972. That was actually a little bit before the accelerator reached its design energy. The experimental program began when an experiment called E36 began taking data. And E36 is noteworthy not just for being the lab's first experiment, but also for being a collaboration between scientists from the US and Soviet scientists during the Cold War. And I think this really shows how important international collaboration has been since the earliest days of the lab. So once the accelerator was up and running, it could be used to send beams of particles to experiments. At the time, there were 3 main experimental areas. In addition to, there was an area called the internal target area, but there were these 3 experimental areas called the meson area, the neutrino area, and the proton area that collectively were called the fixed target areas. And interestingly, each one has a distinctive structure that's associated with it. The proton area has the proton pagoda, the neutrino area has the geodesic dome, and the meson area has the meson lab. And you can see these are all very unique buildings, and the attention paid to the design of the lab was really one of Wilson's influences. In fact, in his drafts for his memoirs, he says that when he had the opportunity to take this position of director of the lab, one of his conditions was he wanted to be given pretty free rein on the architecture as long as he stayed within the allotted budget, because he felt that it was important that the lab have a site that incorporated architecture and things that would be inspiring to the people there and would reflect the importance of the work being done at the lab. And part of the reason for his interest in these sorts of things was that he was a sculptor. You can see here 2 sculptures that Wilson created for the lab that are near Wilson Hall. There's also this sculpture that stands over one of the lab's gates. Another way in which Wilson influenced these aesthetic sensibilities of the lab was by hiring lab artist Angela Gonzalez. And so she was one of the first people that Wilson hired. She was actually employee number 11, which I think also shows just how high of a priority this was for Wilson, that, you know, they're starting this accelerator laboratory and the 11th person that he hires is the lab artist. And she worked at the lab for many years into the 1990s. And she chose the bold color scheme for the lab, the blues, oranges, and reds. She also designed the lab's iconic logo, which she created by combining the shapes of 2 types of magnets that were used in the main ring accelerator, dipole magnets and quadrupole magnets. You can see on this image, the number 1 is a dipole magnet and the number 3 is a quadrupole magnet. She also designed these really striking publication covers and posters for lab events. So this is really something that's very unique about the lab, having this legacy of this beautiful artwork that she created for the lab. In addition to bringing an aesthetic sensibility to the lab's buildings and publications, Wilson was also interested in the natural environment of the site, preserving what was on the site and restoring the natural environment of the site as well. Here there's a clipping from the lab newsletter in which Wilson urges employees to please not unnecessarily cut down trees. He had certain roads on site rerouted to avoid having to cut down certain trees. And the lab held its first Arbor Day on May 2nd, 1969. And so this was the spring right after lab employees had moved onto the site. So I think, again, this just really shows what a high priority this was for them, even as they were trying to design and build this really complex machine. They also, you know, took the time to have an Arbor Day. And of course, I can't talk about Fermilab, especially Fermilab's site in the natural environment, without talking about the bison. As you may know, there's a herd of bison that lives on the Fermilab site. Wilson had the first ones brought to the lab in late 1969. It started with the 6 animals that were purchased from Colorado, and then the next year, a larger group came from another herd in Illinois. This was in part about restoring the natural environment that once would have been there where the lab was located. But it also was part of Wilson's enthusiasm for the idea of the frontier. Like many, he saw science as a new frontier, and so he incorporated a lot of frontier imagery into the lab. And we, of course, still have the bison today. There's a photo of them from 2016, and they're still there today. Another important element of the natural environment on the lab site is the prairie. So in 1974, at the urging of Robert Betts, the lab began this prairie restoration effort. This was one of the earliest efforts of its kind and involved bringing native prairie plants back to the lab site and planting them and trying to restore this tall grass prairie that once would have covered so much of the state. The lab began by restoring prairie inside that land encircled by the main ring, and later expanded to other areas. And by the late 1980s, this was home to one of the largest restored prairies in the world. So one of the most iconic structures on the lab site is, of course, Wilson Hall, which was originally called just the Central Laboratory Building. Construction on that began in 1971. It was designed by architect Alan H. Ryder, but Wilson did have a lot of input on the design. He had been inspired by cathedrals he saw in France, and he wanted a building that would rise over the landscape like that and be a focal point for this large, sprawling site. He was also inspired by the atrium in the Ford Foundation building in New York, and he wanted a space that would have trees even through the Illinois winter. So this building was completed in 1973. And not long after it was completed, on May 11th, 1974, the lab held its dedication ceremony in front of this new building. So this is when NAL became Fermi National Accelerator Laboratory. And internal publications almost immediately started using the term Fermilab to describe the lab. It was named in honor of Enrico Fermi, a talented experimental and theoretical physicist who had left Italy for the US just before World War II. He spent much of his career at the nearby University of Chicago, and he played a key role in the Manhattan Project. And Laura Fermi, Enrico Fermi's widow, spoke at the dedication ceremony. So one of the lab's first major scientific milestones was the discovery of the bottom quark by experiment E288. Scientists had theorized that there was this particle that they called the bottom quark, and the paper announcing the discovery was received by publishers on July 1st, 1977. One of the leaders of this team was Leon Letterman. You can see him there in the upper right. You might remember I mentioned him already in connection with that truly national lab idea. The other thing I want to point out in these images is just look at the size of the experiment team here. It's roughly a dozen people or so. And I want you to keep that in mind. It's a similar scale to that first experiment collaboration that I showed. And you'll see as the lab's history goes on, how these collaborations get larger and larger. So this is something you'll see a few times. This is something called the standard model. This is a chart that physicists use to represent the most basic particles and forces in the universe. I like to describe it as being a little bit like the periodic table of the elements, if you're familiar with that from chemistry, except this describes much more fundamental building blocks. And so that's the symbol that represents the bottom quark. And so this is one of the particles on the standard model that was discovered by Fermilab. The next phase of the lab's history was something that was originally called the energy doubler. This is a drawing of that planned energy doubler by Angela Gonzalez, the artist I mentioned earlier. So as early as the summer of 1967, Wilson had talked to his staff about the possibility of one day increasing the energy of the accelerator they were building by using a technology called superconducting magnets. Superconducting magnets are basically magnets that are kept very cold, which lets them run more efficiently and so produce more powerful accelerators. When the lab was building the main ring, they deliberately designed it to allow for this future upgrade. The main ring achieved its design energy on March 1st, 1972, and the very next day, Wilson had his staff begin working on plans for this energy doubler. And then in 1976, the lab held its first meetings about the possibility of adding a collider to this planned accelerator. And the collider would basically create a beam of antiprotons in addition to the existing beam of protons, and would then collide these two beams together, which would produce even more energetic interactions for the scientists to study. So while this project was underway, Wilson decided to leave the lab. He submitted his resignation on February 9th, 1978, and the central laboratory building was named Wilson Hall in his honor on September 18th of 1980. Fortunately, the lab was left in the very capable hands of Leon Letterman. I already mentioned him in connection with the truly national lab idea, with the bottom quark discovery, so he had a lot of ties to Fermilab. He had done research on neutrinos in the early 1960s, and he and his colleagues actually proved that there was more than one kind of neutrino, work that would later win them the Nobel Prize. And this would also be something that would be very important in Fermilab's later program, these multiple types of neutrinos. Letterman also had a sense of humor. I particularly like this image on the right, where you can see that's Robert Wilson wearing a shirt that says founder and Leon Letterman wearing a shirt that says flounder. And in addition to being a skilled scientist and administrator, Letterman was also passionate about science education, and he was involved in many science education efforts. One that I want to mention is Saturday Morning Physics. This was started in 1980, and it still goes on today, and Letterman was instrumental in helping bring this about. And in Saturday Morning Physics, Fermilab physicists teach a series of physics courses for local high school students. And in acknowledgement of all of Letterman's work in science education, later on, after he had stepped down as director, the Science Education Center would be named in his honor as Fermilab's Letterman Science Education Center. It was named for him in 1992. But to go back to this energy doubler project, the lab continued to work on this under Letterman, and it eventually became known as the TeVetron. The Department of Energy authorized its construction on July 5th, 1979. It was the world's first superconducting accelerator, and in its final form, it was a superconducting accelerator and a proton-antiproton collider. It used the main ring to supply the beam of protons and something called the antiproton source to supply the beam of antiprotons. It consisted of about 1,000 magnets that were installed in the existing main ring tunnel. So the TeVetron was dedicated on October 11th, 1985, and the first collisions were observed just a few days later on October 13th. The TeVetron was a very significant scientific and engineering achievement. And here you can see Rich Orr, Dick Lundy, Helen Edwards, and Alvin Tollestrup, who were some of the main people involved in bringing about the creation of the TeVetron and the operation of the TeVetron. They received the 1989 National Medal of Technology for their work on the TeVetron. So I mentioned that it was a collider. These collisions happened in two locations where there were two detectors placed. One of the detectors was called CDF and the other was called D0. The beams, these proton and antiproton beams, would cross paths thousands of times every second at each detector. And every second there were millions of particle collisions being observed. You can see here the detectors themselves. I like these images because it shows you the scale of these detectors. You can see the people standing near each of them, gives you a sense of just how large the detectors physically were. But it wasn't just that the detectors themselves were large, it was also that the collaborations that worked with these detectors were also very large. At their peak, each one had over 500 physicists from many different countries. These photos are not even the entire collaborations, just parts of them. And so compare this to the team that discovered the bottom quark, and you can see how, continuing to push at these frontiers of knowledge takes ever larger teams of people. And this is only, this isn't too much more than a decade later. So Letterman won the Nobel Prize in 1988 with his two colleagues for his work with neutrinos, and he stepped down from the directorship shortly afterwards. At that point, John Peoples became director of the lab. He had first come to Fermilab in the fall of 1971, and he had held a number of important positions at the lab and had played a key role in the TeVetron. So one of the lab's main accomplishments that the TeVetron enabled was the discovery of the top quark. The top quark, like the bottom quark, had been predicted by theory. It was the final quark in the standard model, and the CDF and D0 experiments had hunted for it for years. The discovery was announced on March 2nd, 1995. You can see here Ramsey Auditorium at Fermilab filled with people waiting to hear the announcement. And this is a representation of these proton-antiproton collisions that produced the top quark. So here's that standard model image again. I've still got the bottom quark highlighted because that was discovered at Fermilab in 1977. And now the top quark has also been discovered by Fermilab. So this is another contribution to the standard model. So just as the seeds of the TeVetron were being discussed before construction even began on the main ring, Fermilab scientists were already thinking about how to improve the TeVetron in the mid-1980s. Initially, the old main ring was used to supply the TeVetron with protons, but a new proton accelerator called the main injector was designed to replace that old main ring. So the groundbreaking for the main injector happened on March 22nd, 1993. And here you can see that completed. It was completed in 1999. So that big circle is the main ring, and that oval shape that you see alongside it, that's the main injector. The main injector is about 2 miles around, and this accelerator the lab still uses today. And this is still a very key part of the lab's accelerator complex. So I've been focusing for most of this talk so far on experiments using particle accelerators, but Fermilab is also heavily involved in particle astrophysics, which uses observations of the cosmos to study fundamental particles and forces. The theoretical astrophysics group was formed at the lab in 1983, and particle astrophysics was a young field at the time, and scientists at Fermilab really played an important role in shaping that field. Their work examines what the properties of the smallest pieces of the universe can reveal about its beginning and overall structure. And one of the lab's first major particle astrophysics efforts was the Sloan Digital Sky Survey. This was an international collaboration. It began in 1993 and used a telescope based in New Mexico to create detailed maps of the universe. The Sloan Digital Sky Survey telescope began making its first observations in May of 1998. And John Peoples, Fermilab's director, became director of Sloan Digital Sky Survey from 1998 to 2003. Another interesting thing I like to touch on from roughly this period of time is this development from the early 1990s. Of course, the World Wide Web was just getting started, which, as some of you may know, emerged from particle physics. But Fermilab had one of the earliest websites in the United States, and this is Fermilab's first website from 1992, which was actually a website for the computing division. So Mike Witherell became the lab's director in 1999 and was director until 2005. And when he became director, there were some changes on the horizon because CERN, a European particle physics laboratory near Geneva, Switzerland, was building the Large Hadron Collider. Construction on this accelerator had started in 1998, and this was set to become the world's most powerful accelerator. It would be a superconducting proton-proton collider. Fermilab was actually very involved with this effort. Fermilab scientists helped design and build some of the accelerator's magnets. But having the LHC on the horizon meant that Fermilab would need to shift its focus a little bit because many of the experimenters who needed the kinds of particle collisions created by the TeVetron and the LHC would want to use the more powerful LHC for their research. So one of the ways in which the lab did this was to start focusing more on studying neutrinos. Now, Fermilab had done research on neutrinos since its earliest days. There, of course, was that fixed target area, even called the neutrino area, but now they would become a more major focus of the lab. And neutrinos are very unusual particles. If you've tuned into anything from Fermilab before, you've probably heard about neutrinos, but there's about 100 trillion of them that pass through you every second, and yet they're very elusive and very difficult to detect. They're the most abundant matter particle in the universe, but we know relatively little about them. And to study them, you need to produce a lot of them. So in order to enable the lab to do groundbreaking neutrino research, the lab built something called NUMI, the NUMI beam, which this stands for neutrinos at the main injector. This uses the main injector proton beam to generate the world's most intense high energy beam of neutrinos. So work on this began in 2000 and was completed in 2005, and this set the stage for a new generation of neutrino experiments at Fermilab. The first of these was MINOS, which stands for Main Injector Neutrino Oscillation Search, and used the NUMI beam. And this was the lab's first long baseline neutrino experiment. A long baseline neutrino experiment is a type of experiment that sends an intense beam of neutrinos a long distance through the Earth. And the reason that you do this is to study one of the most interesting properties of neutrinos. So there's 3 types of neutrinos, but over time, those types of neutrinos can change into one another. And this phenomenon is called neutrino oscillations. And these types of experiments, these long baseline neutrino experiments, would become an important part of Fermilab's future experimental program. So MINOS used two detectors, one that was located at Fermilab at the source of the neutrinos, and the other was located 450 miles away in northern Minnesota. The groundbreaking for the detector hall in Minnesota happened in 1999. The experiment started running in 2005 and ended in 2016. And I like to share this image of the FAR detector hall because there's this really beautiful mural on the side of the space. And I think this is just another nice example of how art often goes hand in hand with science with Fermilab. So during this time, Fermilab made another milestone discovery when the donut experiment observed the tau neutrino. Donut stands for direct observation of new tau, and new tau is a way of saying the tau neutrino. This discovery was announced on July 21st, 2000. So here's the standard model again, with still the bottom and top quarks highlighted because they were discovered at Fermilab. And now the tau neutrino has also been directly observed for the first time at Fermilab. In 2005, Mike Witherell stepped down as director and was replaced by Piero Done, and he served as Fermilab's director until 2013. The Large Hadron Collider was completed shortly afterwards in 2008. It contains about 10,000 magnets and is about 17 miles around compared to the TeVetron's roughly over 1,000 magnets and 4-mile circumference. So it's a much larger scale machine. And one of the major experiments at the LHC is the CMS experiment, the CMS detector. CMS is similar to CDF and D0 in the sense that it's a collider experiment, but it's larger. You can see in this photo, you can see that little tiny person, down at the bottom there, really gives you a sense of the scale of this detector. I was lucky enough to get to see it in person once, and it's really very, very impressive. And it's also very large in the sense, not just of the detector itself, but again, the collaboration. It has well over 2,000 members in this international collaboration compared to CDF and D0, which each at their peaks had around 600. And the reason I'm talking about CMS in some detail is because Fermilab is actually heavily involved in CMS. When you have an experiment this large, these sort of particle physics experiments are international efforts with, thousands of scientists from all over, and that includes from Fermilab. Fermilab provides support for the hundreds of scientists from US universities and laboratories who work on CMS. Fermilab also helps process data from CMS. It's a tier 1 computing center for CERN. And Fermilab has a remote operations center where scientists can actually conduct remote shifts at CMS from Fermilab. So shortly after the LHC was up and running, the TeVetron was shut down on September 30th, 2011. Helen Edwards, who played a key role in the design and operation of the TeVetron, she was one of those who won that National Medal of Technology. You can see her here hitting the switch to turn the TeVetron off for the last time. So you may remember from 2012, there was this big news about the discovery of the Higgs boson. This was another long sought after particle, and it is responsible for giving other particles mass. And this discovery was announced by the CMS and ATLAS collaborations at CERN on July 4th, 2012. And again, Fermilab scientists played key roles in this discovery. This particular image is a simulation of one of the collisions observed at CERN. And so here's that standard model again. And that is the representation of the Higgs boson, which Fermilab contributed to the discovery of that. So during this time, Fermilab's involvement in astrophysics was also continuing. Fermilab was involved in the dark energy survey starting in 2003. This is also an international collaboration, and it uses a camera mounted on a telescope in Chile to survey the sky to investigate the effects of dark energy. And one of the reasons I like talking about the dark energy survey is because I like being able to share one of the images that the dark energy survey's camera produces. It started taking pictures in 2012, and this is an example of one of those really incredible images that it produces. So our current director, Nigel Lockyer, stepped into the position in 2013. He was director of TRIUMPH, Canada's National Laboratory for Nuclear and Particle Physics, before coming to Fermilab. And in the last few years, Fermilab has continued to focus on neutrino physics, among other things in its experimental program. The NOVA experiment represents the next generation of long baseline neutrino experiments after MINOS. It also uses the NUMI beam, and it's Fermilab's current flagship neutrino experiment. And like MINOS, it studies neutrino oscillations. And here you can see the NOVA near detector, which is at Fermilab, and then the NOVA far detector, which is in Ash River, Minnesota. The detectors were completed in 2014. And again, there's some people near the detectors that kind of gives you a sense of the scale of these detectors. Even the near detector is quite large, but then of course it's dwarfed by that far detector. And then to look a little bit at the future of the lab, there's LBNF, the Long Baseline Neutrino Facility, and DUNE, the Deep Underground Neutrino Experiment. And these represent some of the future of the lab. This is another long baseline neutrino project. LBNF will be an internationally designed, coordinated, and funded program. And DUNE will use an upgraded neutrino beam that will be the world's highest intensity neutrino beam. The near detector again will be at Fermilab, and the far detector will be at Sanford Underground Research Facility, or SURF, 800 miles away in South Dakota. So this is again upping the scale of these types of experiments. And DUNE will help scientists understand things like why there is more matter than antimatter in the universe and other fundamental properties of the universe. So the DUNE collaboration officially formed in 2015. It already has well over 1,000 collaborators from all over the world. So again, it just shows how the scale of these experiments keeps increasing. You know, we went from these small, dozen so people teams for things like the discovery of the bottom quark to then you have, several hundred for the teams that discovered the top quark, and now to push into these new areas, you need even larger teams of people. And the groundbreaking for LBNF was held at Sanford Underground Research Facility on July 21st, 2017. It actually was sometimes called an underground breaking because you can see the construction is actually happening underground because another aspect of these neutrino experiments is that you need those detectors to be underground to help shield them from interference. Another important part of the lab's current projects and future is the PIP2 project, or the Proton Improvement Plan. This will replace the lab's current linear accelerator, the LINAC, with a superconducting one. So if you remember that groundbreaking that you saw on that snowy, December day back in 1968, well, that same LINAC has still been used as part of the accelerators complex. It's been upgraded, but it was still that same LINAC. And so just like upgrading from the main ring to the superconducting TeVetron ushered in a new era at Fermilab, this new superconducting LINAC will open up many new doors for scientists. This PIP2 project will also refurbish other parts of the lab's accelerator complex, and this is what will ultimately make the DUNE experiment possible. So you can see here a little bit of how those beams will work. So while Fermilab has frequently hosted experiments and detectors with strong international involvement, PIP2 is noteworthy for being the first accelerator project in the US that will have significant contributions from international partners. And here you can see where that PIP2 facility will be located near Wilson Hall. So there's so many other experiments and aspects of the lab's history that I couldn't cover. I really would highly encourage you to go to Fermilab's website and learn about some of the other elements of the lab's experimental program and the other accelerators at the lab. There's a lot of really exciting experiments and work going on at the lab. If you're interested in the lab's earlier history, I would highly recommend this book, Fermilab Physics, the Frontier in Megascience, by Lillian Hoddeson, Adrian Cobb, and Catherine Westphal. This really gives the detailed story of the origins of the lab and the creation of the main ring, the TeVetron, and goes up through the discovery of the top quark. So thanks again for coming, everyone, and let me know if there are any questions.
Well, thank you, Valerie. That was an excellent presentation. We do have one question from Robert, who would like to know if the model airplane field is still used, at least before COVID.
So I'm not 100% sure. I know right now with COVID, the lab site is not open to the public. I'm not sure how actively it was being used before then. But if he wants to, I can share my screen again and put my contact information up. If he wants to reach out to me, I can look into that.
Okay. I do know there's still a windsock out there, so it's usable anyway. All right. Well, we'll now take a 30-minute driving tour of the Fermilab campus. And if you have any questions along the way, please type them in the chat. Our guide for the tour is Laura Paterno, an education facilitator at Fermilab. It's all yours, Laura.
Looks like we have a few more questions, Rick, for Valerie before we start.
I didn't.
A couple just came in last minute.
Okay. Dale, no, you cannot ask with audio. You need to put them in the chat. Valerie, what's the title of the book that you mentioned?
So it's called Fermilab Physics, the Frontier in Mega Science.
Okay.
I've put the title up there on the screen.
Okay, and from Amanda, is there a project as Fermilab's archivist that's been your favorite, or any parts of your job you didn't get to share that is your favorite?
I have to say, I think my favorite collection that I've worked on was actually the Angela Gonzalez collection. I very much enjoy art, and I had worked at the Art Institute, and so that was a really fun thing, going through her artwork and seeing it all and organizing it. So there's been lots of projects that I've really enjoyed, but that one really stands out in my mind. And I was involved in organizing a nice exhibit of her work during the lab's 50th anniversary here.
And from Kitty, and something we all would like to know, when will Fermi be open to the public?
Yeah, that unfortunately I don't know, but I'm sure as soon as it is, the lab will announce that.
Let's see. Can you explain, from Neil, can you explain the story of how the Batavia site was not chosen for U.S. high energy accelerator that eventually went to Texas and was abandoned down there?
So that's a long story. What I would recommend, there's a book called Tunnel Visions that I'm trying to remember all the authors on it, but one of the authors is Adrienne Cobb, who was also one of the co-authors on that Fermilab book, and she's a former Fermilab archivist. Tunnel Visions really goes into the details of that story because it's a long one.
Okay. And do you know if the Saturday morning physics was recorded during COVID?
Maybe Amanda can answer that. I'm not sure.
It was. I can put a link in the chat for the those lectures. Happy to do that.
Okay, great. Let's see. That's all the questions I've got here. So Laura, if you're ready for the driving tour, it's all yours.
All righty. Good afternoon, everyone. And as Rick said, my name is Laura, and I'm an education facilitator here at the lab, and I will be your tour guide today as we take a driving tour around the complex. Due to the amount of time that this video due to the amount of time that it takes to actually drive around to certain parts of the laboratory, the video has been shortened to account for that. So get your seatbelts fastened and let's start our tour. And I'm going to stop my video and Amanda will start playing our video for us. So we're going to be starting our tour here at the main entrance of Fermilab, going under broken symmetry. The sculpture is designed by our first director, Dr. Wilson, as Valerie talked about in her talk. The sculpture is made with the remnants of steel from a decommissioned Navy aircraft carrier called the USS Princeton. It weighs 42,000 pounds, or about 21 tons, and rises about 50 feet above the road at its apex. And ordinarily we would have stopped at that guard gate, but we had special permission to drive through. Ahead on our right there are some of the buildings from our neutrino research area that we're going to be visiting later. Right now, I'm going to talk about that Fermilab is a 6,800 acre facility, about 10 square miles. Our site contains most of the major Midwest ecosystem types, and in 1989 was designated as a National Environmental Research Park, one of only 6 across the country. About 1/6 of the site is restored tallgrass prairie, and we are driving through a portion of that prairie right now. You'll notice that there were some woods off to the right. Just beyond those is the next building that we're going to be seeing. That is the Letterman Science Center, named after Dr. Leon Letterman, our second director. It is the hub of many of our education and public engagement programs, some of which utilize the natural areas of the lab that we'll be passing through. The Letterman Science Center has hands-on exhibits, a science lab, a maker space, and a gift shop. In addition, we host classes, field trips, and tours for both students and the public. And you may have noticed that as we've been driving, our road is curving and continues to curve through this wooded area that we are approaching now. Dr. Wilson, because of his passion for the environment, and directed that as much as possible of the original wooded areas on site be preserved. So several of the older trees on site were spared from being cut down by curving this road around, and this reduced the number of trees that was going to be cut down in this area here in particular. There are some ponds that we're about to be approaching on the right-hand side, and those ponds were used to cool the heat generated by the electromagnets used to steer and focus our particle beams here at the lab. They also attract a large variety of waterfowl that migrate to or live in this area. When the TeVetron was running, the ponds were filled almost every day with birds who liked to rest in the water that was warmed from that cooling process, and there was frequently steam coming up from the water. Behind the pond, you can see the central hub of our site, which is Wilson Hall. And if you've been here before, you may have noticed some of the changes that are happening here at the site. You can see the IERC building off in the distance, which I'll talk about in a minute. We're about to turn to go towards Wilson Hall, and as we turn, you'll get to see another sculpture that Dr. Wilson created. It is called Aqua Ale Fune, and it was his parting gift to the lab. So Wilson Hall, ahead of us now, is our central building on site. It is 16 stories high and contains offices, laboratories, remote experiment control centers, an art gallery, meeting spaces, and a cafeteria. It is attached to the Ramsey Auditorium in the back, which seats over 800 people. The auditorium is used for physics lectures and conferences, but it is also used for a public lecture series and art events. And you may notice as we are approaching and as we turn to stop for a minute to actually view the lower portion of the building, that you can see through from the back to the front. Most of the office spaces in the building are on either the right or left side, and there are some on the higher level floors at crossover points, but the central area Dr. Wilson left open particularly, and the atrium area, as we call it, goes from the floor to the ceiling, so over to the 15th floor. To our right here, you can see one of our newest buildings that's under construction. This is the Integrated Research Engineering Center, or IERC for short. This building connects directly to Wilson Hall, and it will provide a space under one roof for our engineering specialists to work more closely with each other and with the personnel who work in Wilson Hall. You may remember from one of Valerie's slides that there were flags on these flagpoles before. They were not up today or the day we recorded this video. They hold the flags of the countries who participate in experiments here at Fermilab. Currently, there are over 40 countries that participate, and we rotate those flags throughout the year and in the atrium. As we swing around here, we're seeing the west side of Wilson Hall, when we come to the start of our accelerator chain, our particle beam begins in that small squarish building to the left with a bottle of hydrogen, and then runs through what's called the berm here, through our linear accelerator down to our booster accelerator. Particles, when they leave our linear accelerator, reach about 70% of the speed of light, and their energy is about 400 million electron volts when they hit the end. At the end of the linear accelerator here, the particles are transferred into our booster accelerator, which is a circular accelerator. The smoke that you see coming up there comes from the water treatment plant that provides deionized cooling water for our magnets in the accelerator. When particles leave the booster, they are at 8 billion electron volts, and they travel at over 98% of the speed of light. And across from our booster accelerator, which is right there, we are going to visit our muon complex. This first experiment in our muon complex, or this first building, will house our mu-to-E experiment that is currently under construction. The goal of this experiment is going to be to determine if the fundamental particles like muons can spontaneously convert into electrons. The building next to it houses our muon G-2 experiment, which has been in the news lately. The muon storage ring is about 50 feet in diameter, and it is a precision superconducting magnet. They use the magnet to measure the spin property of muons. They recently released their first results, which has caused quite a bit of excitement, and you can check out our website for more information on that. We're going to continue driving towards that big accelerator ring that Valerie was talking about, which is 4 miles in circumference. This is where both the main ring and the TeVetron were located, approximately about 30 feet below the berm that I talked about. Berm is a term in general used to talk about the area that covers over accelerators here at the lab. And you may notice that when we reach the top of the berm, that there are pipes containing cooling water that are, those cooling water that I was talking about that remove the heat generated by our big electromagnets in the main ring. So you sort of could see them for a few seconds. So inside the main ring is also that first Prairie Restoration that Valerie talked about, that Dr. Robert Betts, who was from the Northeastern Illinois University, helped to establish and maintain. And to our left, you're going to see something that Valerie just showed in a graphical form, but is now actually partially built. So this is part of our PIP2 project, or Proton Improvement Plan. And it will replace the existing LINAC, as Valerie said, and be the foremost facility in the world for particle physics research using intense beams. This is one half of it. This is the cryo building for PIP2. There will be another building in back as well where the accelerator will be housed. Protons from a hydrogen source will be formed into a beam and accelerated by superconducting radio frequency cavities. Particles will go from 7% of the speed of light to 84% by the time they reach the booster ring, when the accelerator turns on in hopefully about 2028. The beam's power will go from 1.2 megawatts to a later upgrade of about 2.4 megawatts. And PIP2 is being built with significant international participation in it. So it's a first of its kind here at the laboratory, because we are now combining with many countries outside of the US to do this. The new accelerator will enable the production of an extremely intense neutrino beam for our flagship experiment, DUNE. And I'm going to be talking more about that as we pass by DUNE. On our left here in a second, we'll see the back side of Wilson Hall. So this is the east side of Wilson Hall, and this is also the east side of our Integrated Engineering Research Center, or as I said, IERC for short. We're about to pass by a small block-like building that is white in color. And this is one of the access points into the old accelerator. Not that, that is obviously just a simple, this is what I'm talking about here. That was an access point, and one of many access points into our accelerator ring. The white building that's coming up on the left as we get past another access point here is our Feynman Computing Center. And I'm going to be describing more about that later, but we're getting a nice view of it right now after we pass by the construction over here. And there it is. So this is home to some of our computing division and some of the data that we collect experiments for on site, and I'll talk more about it later. We're about to pass by some big orange tanks past this access point again. Those orange tanks were filled with the helium gas that was used to cool the superconducting magnets in the TeVetron. And we are approaching our IARC building now, where scientists and engineers at IARC, which stands for Illinois Accelerator Research Center, work side by side with industrial partners to do research and develop breakthroughs in the accelerator technology and translate them into publicly available products and services. Pay attention to that cart that just went past. I'm going to be talking about that in a little bit, so I'm giving you a little preview. As Valerie said earlier, when Fermilab was first built, the first accelerator in the tunnel was called the main ring, and it was the most powerful accelerator in the world. Its designed energy was 200 billion electron volts, but it eventually, as Valerie said, achieved 500 billion electron volts. And in 1985, the TeVetron replaced the main ring, and the TeVetron was named after its designed energy of 1 trillion electron volts. It directed the beam using superconducting magnets, and protons circled the ring clockwise and antiprotons circled the ring counterclockwise. The two beams collided in the centers of the CDF and D0 experiments that Valerie mentioned. Both experiments discovered the top quark in 1995, and that's one of the fundamental particles of nature. And we have driven about halfway around right now, and this blue building in front of us is D0. And now we're looking inside the main ring at where the first Prairie Restoration site was. And you'll notice off to the right, if you saw it really quick, that there was some smoke going over there. And here it comes. That is a prairie burn that was happening as we were videoing this. The oldest restored prairie site is in the center of the main ring, and the smoke that we saw there is from a prescribed prairie burn. Burning is necessary to maintain our prairies here on site because the ash distributes nutrients back into the soil. The burns at Fermilab are supervised by our resident ecologist, our roads and grounds crew, and the Fermilab on-site fire department. A fire break is currently being created around the burn area right now, so we'll keep an eye on that as we progress throughout the site and see how that burn progresses. And the red barn that we are passing is one of those original buildings that was on site that we have maintained and kept. So we just completed the 4-mile drive around the ring. That burn is going pretty strong right there. And we're going to go past our booster ring and our muon experiments towards our neutrino experiment areas. So here we are going past the muon experiment. There is actually a surveyor on the hill up here. You can just make him out, who is doing some surveying probably for that PIP2 project to do the connection point. And we are passing now by the old antiproton area that Valerie had mentioned, where antiprotons were created from proton collisions with a target. The current use of that area is now to provide a muon beam to those muon experiments. So now we're getting a glimpse of some of the new neutrino areas on site. So this is one of those areas, but I'm going to take you a little bit past this first, and we're going to come back to it. So the property that we're going to be seeing past this on our right will be the site right here in this area coming up of our on-site, so short baseline experiment for the Dune experiment. Our new PIP2 accelerator will help create an intense neutrino beam. This beam will pass through an underground detector located here, and then it will travel that 800 miles directly through the Earth to the detector for Dune in Leeds, South Dakota. This will be a very big detector that will hold roughly 70,000 tons of ultra pure liquid argon and will be located a little over a mile underground. And physicists will use this data from these detectors to shed light on some of the mysteries that Valerie was talking about. So now we're going to turn around and get another very nice view of that prairie burn that has now expanded a little bit. You can see that more of a burn is happening around as they establish that fire break in the prairie burn. And we are going to go back towards our neutrino area. Fermilab will be hosting 3 neutrino experiments, which will make use of a shorter beamline of neutrinos than the Dune experiment will use. The short beam will pass through the 3 detectors sequentially. So these detectors are needed to study neutrinos at different distances from the target where the neutrino beam is produced. So this area that we are approaching right now, right past where the curve is, that is a shed for protecting some of the equipment for the short baseline neutrino near detector, which is right behind it. And this is the first in that line of 3 neutrino experiments. So we're going to drive past this area right here, and then we'll go on to our next 2 areas and see them in just a second. So this building right here is the short base, where the short baseline neutrino near detector, or SBN-ND as an abbreviation, will be housed. And the detector itself will be underground. So this next building that we are seeing right here is the liquid argon test facility, and it houses our second detector, which is called Microboon, and Microboon is underground in this building. They also recently published some interesting results, which you can again find on our website. The third detector in our short baseline area is the silver gray building that's just off to the left that we'll see in just a second. And the 3 detectors, when combined, will be searching for a strange particle called the sterile neutrino. The building to the left of the gray one is the on-site access point for our NOVA experiment. It's a neutrino beam is sent from Fermilab 500 miles north to Minnesota for this experiment, and the NOVA experiment and also the NINOS and other neutrino experiments on site reside in that building. So if we could pause, Amanda, real quick, and see if there's any questions that I might be able to answer, or if there's any questions I need to answer.
There are no questions, Laura. So if you want to continue.
All right, Amanda, if you want to hit play, we can keep going. So we're now going to go continue east of Wilson Hall towards that IARC building that I was talking about earlier. And our burn is going along really nicely right now. We're about to pass by that Feynman Computing Center that I was talking about. That houses a vast amount of our experimental data here and also in additional sites on the property. Both CDF and D0 recorded over 10 petabytes of data each, and that is stored in this building and is accessed through robotic tapes. We have the capacity to store over 600 petabytes worth of data on site, and currently have over 100 petabytes worth of data stored on site. We store experimental data for some of our CMS experiments, for the CMS experiment, as well as for experiments on site here. We're approaching the IARC building, and anyone working in there right now has a great view of this burn. We're seeing all the smoke. They get to see the flames as well. At the ends of this building, you can sort of see a little bit right now. There is some orange there. That orange is where the CDF experiment that Valerie talked about, part of it was existed there. This area here was the CDF experiment area and was replaced when IARC was built. We are going to go into our industrial building complex right now. And these buildings here are used for building and testing equipment like our magnets here, and also for what's called our radio frequency cavities. They do both building and testing here, and these are used on various sites, both on and off the property. This is also an area where we are currently starting up a bunch of quantum research. This is right here, another experiment, not experiment. This is another sculpture Dr. Wilson created. It's called Tractricious, and it's made from leftover cooling pipes. Many of his sculptures were actually made from leftover remnants of projects built on site. Now everyone's favorite to see, we're driving past the Bison really quick and we can see they're out there, and we're going to stop by and see them a little bit later as we proceed. But you get a nice view of them right now. It's close to feeding time, so they're close to the barn right now. They don't actually go in the barn though. You can see that there is a large amount of open space and land areas on the site. Some of the land is leased by local farmers, and some of the areas are used for environmental studies, as we are a National Environmental Research Park. We are now approaching the Fermilab Village. And these houses that you're seeing right here are the houses that Valerie was talking about that were originally owned by farmers on the property, and that has now been moved over into our Fermilab Village area. So this is one side of the village. The other side of the village is where the town of Weston was, that we'll see briefly as we get to the end of our circle here of where the former houses, former owners' houses were. So that is looking now towards where Weston used to be. And we'll get a brief glimpse of those houses and the colorfulness that Angela Gonzalez added in. There's blue and oranges houses over there, and those are part of those original Weston houses that were on site. So our prairie burn is going strong over there now. We're going to head now towards our fixed target area that Valerie had talked about earlier. So that is that meson, proton, and neutrino area, which was where our earliest experiments were. You can imagine that with all this open land that we do have a wide variety of wildlife on the property, and they roam around many of the areas that we have been driving through right now. So we are now passing by the bison pasture again, and we're going to take a brief second here to stop and get a chance to see them. As I said, it is they are eating right now, so we'll get a brief second to be able to see them actually eating. This was recorded just a couple of days ago, so this is very recent. You can see there they are off eating away. Most of them are actually in the fencing area behind there. They don't, however, go into the barn. They are outdoor creatures, and they are not in the barn very often at all. And since they're being a little camera shy and they want to stay over there and eat, we're going to leave them and continue towards our fixed target area. So this is more of the pasture where the bison just roam between the enclosed areas of our pastures. And off in the distance, you can see this building, which is our proton pagoda. So Valerie had pointed this out earlier. This was the control center for our proton area. Now we're driving down the meson area, and we're driving between the meson and the neutrino area that Valerie described. And these are pi poles. This was another thing that Dr. Wilson requested our local power company to make poles the shape of the symbol pi. To the left, there is our Meson lab that is now our test beam facility. Researchers from around the world can come here and test their experimental components before putting them in their projects. So they can do simple tests or complicated tests in here. All they have to do is request access to this test beam facility in order to do that. You may have noticed that there was some smoke behind the test beam facility. That is another prairie burn going on. However, that is not being conducted on site. That is actually off site to the lab. So these are more of those pi poles. They were originally made out of wood, and they were replaced in about 2004, 2005 with steel poles. Stainless steel poles, so they will hopefully last us a very long time on the property. So we're going to head now towards our silicon detector area, also called SIDET. We're just going to get to the end of our long road here to the turning point to get to SciDet. And we're going to start at the back end of SciDet actually by looking at that apparatus right there and over here. So this building over here is SciDet. That apparatus was called a bubble chamber, and it was one of our earliest experiments. It's the main detector in the fixed target neutrino beam, and it was filled with liquid hydrogen. The buildings surrounding the bubble chamber there are filled with clean rooms and labs for the purposes of now developing silicon-based components for detectors and telescopes. You can't see, but there are actually beautiful diagrams in the areas above where the windows are. Ahead is the FAST facility, which stands for Fermilab Accelerator Science and Technology. It's the home of IOTA, a small innovative accelerator used for testing accelerator design components. And to our left, we're going to see the front of the SciDet building and that dome building that Valerie referred to earlier as the neutrino geodesic dome. That area is now used for assembling telescope equipment such as DCAM, which was the imaging device for the dark energy survey, because it has a high ceiling assembly area in it that allows for that sort of construction to happen there. And now we're at the back end of that Mason area that we were talking about, driving around the back end of the test beam facility. The roof of the test beam facility was something that Dr. Wilson wanted to try something unique with. He decided to use culverts to make up the roof of the facility, and we'll get to see a close-up of those as we get there. There are the big curves on the top of the roof that we'll see in a few seconds as we get up to it. You can see the building from the back reminds a lot of people of an airport hangar as we drive past it. And our burn there is going really strongly right now. So now we're approaching the test beam facility, and you'll see now these culverts that I was talking about as we drive past it. Fermilab has a security team on site, and we also have a fire department, a full-time fire department on site. We employ roughly 18 firefighters who work in 3 different shifts, and much of their work is preventative. However, we're really glad to have them on site. Today, they are currently monitoring this burn that we're seeing ahead. And we're going to end the tour back up at Wilson Hall, and we hope you enjoyed this tour. And if you would like any information other than what you've heard today, please check out our website. We also have an education site in addition to the Fermilab site that is at ed.fnal.gov. The Fermilab site is fnal.gov. We are unfortunately not currently open to the public, and we have but we do have many virtual opportunities available that can be accessed through both of those sites. We also have a large presence on many of the social media platforms like Twitter and Facebook and YouTube. And I hope you enjoyed the tour. And if we have any questions, you can put them in the chat now, and I'll be happy to answer them.
We do, Laura. Let's see. Oops, I just lost my chair. Will the Letterman Science Center be open for Christmas? And if not, will it be possible to buy any of the merchandise online?
That is a very popular question that we get asked. The Letterman Science Center itself, as far as I know, will not be open to the public. we are in the process of trying to transfer our online store to a new system, which is why it's taken so long to get it back up online. As soon as it is available, we will let everybody know. It may not be available for Christmas, but we will hopefully have it up by the open house coming up in February.
Okay. And from Waleska, are there any plans to make more buildings for the neutrino experiments?
Yes, actually, the area that I was showing you that was just that empty field, all of that has to be built up for the Dune neutrino experiment. So that is still in the works to come. We're focusing right now on PIP2 and the IRC building that is right behind me on this picture behind me.
And Ibrahim would like to know, where is Dune? So maybe if you could just hit where the short baseline and long baseline things are.
All righty, so off to my right would be where the Dune experiment will sit on site. So it was that empty field that was after we had gone from the main ring. We were driving past a series of small experiment buildings after we had driven around the main ring. It will be in that field there, so it will be inside our main injector. And then the FAR detector will be in Lead, South Dakota, which is about 800 miles from here. And it'll be about a mile underground.
And when's that going to be up and running? What's the guess on that?
The guess on that, PIP2 is going to be operational in 2028, so it will be after that. I don't know how far after that because the schedule has shifted because of COVID.
Okay. And from Janet, do researchers live on site?
We do actually have some who live on site in our village. They are there for typically a brief period of time. If they're staying longer, they're typically staying off site, but we do have several who live on site.
And Neil is saying the remote ends of the various neutrino experiments are not linearly aligned. How many of these far neutrino detectors can Fermilab serve with neutrinos simultaneously?
That is a good question. I do not know the answer to that one. I do not know if I don't think we're going to be sending beam up to Nova and off to South Dakota at the same time. But I do know that we were running Minos and Nova at the same time, and they were in 2 different locations.
And Amanda, Nina is wondering if there's going to be a link to the driving tour that people can access.
Yes, this whole talk and tour was recorded. And in addition, in our open house, we will have a more detailed driving tour as well.
Okay, let's see. And Robert brings up an interesting point. He says, seems like the newer buildings are very functional, but are not so creative architecturally, like a lot of the old ones are.
Actually, when you see them on site, they have a lot of glass in front of them. So there's a lot of reflection that will be happening that you're not seeing right now, because this side that's behind me right now actually does not have the glass in it. But that reflection of the glass with the land adds a beautiful appearance to those buildings.
Okay, well, those are all the questions we have. Thank you to our presenters, Valerie and Laura. That was a wonderful presentation. And thank you all for joining us. We'll see you next month for Ask a Scientist.